Hello, good afternoon. After, I know you enjoyed a hearty lunch and maybe thinking of dozing off, but it is my job and Chintan's to make sure that you don't doze off. So we'll make this session even more interactive than the other sessions that you have seen. That is the plan. And Chintan has come up with a interesting scheme of things, which he will explain a bit later. But while while yeah, having said that, I'd like to invite on the dais Professor Rajdeep Bandyopadhyay. Rajdeep, yeah. So Rajdeep is a professor in the Department of Chemical Engineering in IIT Bombay. He is associated with the Tata Center as a PI for the project detection and sensing of arsenic in drinking water. Next, I'd like to invite Professor Shuparna Mukherjee. Professor Shuparna Mukherjee is a professor in the Center for Environmental Engineering. Environmental Engineering, and she, along with Professor Sanjeev Chaudhary and Anurag Garg, they are involved in the project characterization of grey water and development of a cost-effective system for grey water recycling. Professor James Westcote. He's the Aga Khan Professor in the Department of Architecture at MIT USA. He's involved in 3 projects in MIT Data Center. And believe me when I say so that he knows more about Murshidabad in Bengal. I come from Bengal. He knows more about Murshidabad in Bengal than I do. I mean, he has stacks. I mean, his knowledge about those things are just those places are unbelievable. Next, I'd like to invite Professor Rohit Karnik. Rohit, welcome back to IIT Bombay. He's an alumnus of IIT Bombay, now an associate professor in the Department of Mechanical Engineering in MIT USA. He'll be speaking on how to use plant xylem for filtering water. So, Chintan, come on board and time me. I have taken the prerogative of being the joint chair of this session to put the first 2 talks for myself. Chintan, you're supposed to stop me. This is a lightning presentation in a sense that you are just going to go 3 minutes. Also, at the end of the presentation, you can ask clarifying questions, little bits, but not major long questions, no long comments. We have plenty of time for that, and we'll later on use those boards because we want to make this session as collaborative as possible, and essentially we are trying to crowdsource ideas. Okay, so that is what is going to happen. We'll do it in a much more interactive format. So there are two projects in the water domain that I'm working on. I'm going to go at them one by one. The first one is electrical impedance spectroscopy platform for bacteriological monitoring of water, particularly grey water. And so what is this grey water? It is wastewater produced in households except those with fecal contamination, that means no sewage, which is called backwater. So the sources are hand basin, showers, laundry, and so on. So what this can be used for after a little bit of treatment is toilet flushing, gardening, irrigation, car washing, firefighting, and so on. But the grey water has also some pathogens and organic matter, so some amount of treatment is required before it is actually used. And for various purposes, gardening or irrigation or spraying a plant with water, all of those have slightly different requirements in terms of bacteriological contamination. So the idea is that and now, by the way, grey water recycling is compulsory in every housing society in Mumbai. But the housing societies are putting up grey water plants, but they don't know what's coming out of it, really. Is there a way to give a cheap and inexpensive solution to the housing society so that the grey water quality is maintained and is measurable? So we have developed a sensor based on paper. It is a filter paper with just 2 silver electrodes, and silver electrodes means silver paint by which 2 electrodes are made. We have put this contacting polymer called polyaniline between those two silver electrodes. and looked at the impedance spectrum over a variety of frequencies. And with this, when these bacteria come and attach to the polyaniline, the frequency spectrum changes, the impedance spectrum changes. And that is fundamentally what is being used. And as you can see from this, for different frequencies and as the material count changes, you can see that actually the impedance spectrum also keeps on changing. So that is what we can use. And this is the sensor part is really, really cheap. It's just paper with 2 silver electrodes painted on it and a drop of conducting polymer on it. So it's like what, 20 paisa sort of sensing. The concept is that we are going to use a little add-on to a smartphone to which this paper is going to be paper sensor. Right now it goes with alligator clips, but later on it's going to have a little holder. So that is one. And the other one is a completely standalone thing which has a display over here. So we are still trying to figure out which one is the best user model from the user point of view. And anyway, the frequency range that we use is 10 Hertz to 10 kilohertz and all that. So those can be even generated using a smartphone. We don't have to have our own signal generator for this. So that is one, the EIS spectroscopy-based bacteria. The next one, if I can find it somehow. So we have been working on optical fiber-based sensors for a long time. And while working on it, what we have seen, we have discovered that this conducting polymer called polyaniline, that the spectroscopic nature of polyaniline changes with interaction on the surface. That is something which has not exactly discussed in literature as far as my knowledge goes. So we decided that we will try to use this conducting polymer polyaniline coated on a fiber to sense heavy metals. So of course, everyone knows, I mean, the sources of heavy metals are many, mining, industrial exposure, waste disposal, corrosion, and all sorts of things. And there is arsenic, which if you look at these figures, 10 parts per billion is the maximum that's for drinking water. It's a few drops of ink in an Olympic-sized swimming pool, or 130 million people are exposed to levels of arsenic which exceed this WHO limit. 50 million people have been exposed to more than 50 parts per billion sort of limit. And so we started looking at arsenic as one of those, and we also started looking at mercury and lead. So where is this page down? We use a principle called the evanescent wave absorption. So on the fiber we have coated polyaniline, and on the polyaniline we have put some receptors, which are receptors for these heavy metals. And once the heavy metal binds to it, the input light into this fiber gets absorbed more at a particular wavelength, and that we can detect with a spectrophotometer outside. We can even change the spectrophotometer to a simple filter and a photodetector. It does not have to be a spectrophotometer per se. And so this is the envisaged system device, which is on this. This can be any size given the magnification on the screen, but it is actually about 4 inches wide by about 4 inches tall and about 8 inches long. That is the size of the device. Completely portable, runs off of a power bank with which we keep charging our mobile phones. And what we have seen is that we can detect lead, arsenic, and mercury at very, very low concentrations, down to concentrations of 1.2, 1.73 ppb and things like that. You see, normally if you have to analyze water, you have to send it to a lab. They'll do atomic absorption spectroscopy and all of that and charge 3,000 rupees for this. So this is a 25, 30 rupee version of, and with as good a sensitivity as one can get in those labs. And as you can see that, other things like potassium, sodium, magnesium, or other things which can be there in water does not affect the sensors very much. It is much, much more affected by lead, arsenic, and mercury. So that's all. If you have quick questions, clarifications, please shoot. I guess no questions. So then let me invite.
Good afternoon, sir. Very nice presentation. So my question is regarding to the cost effectiveness. Since you said it's 25 and 30 bucks compared to the 3,000. So what is the customer? What is the people that you are targeting with this instrument, this particular instrument, to have a wide range of applications? Because it's sensing, the chemicals in the water. So if let's say if I'm going to buy this, how much I need to pay and what is the service time to use this? Like how long I can use it? So that was a very simple, question.
Okay, excellent question. This is targeted at a mid-level. This is not targeted towards the individual customer or the housing society. Although the housing society might as well buy it. This is targeted at something like a panchayat or water processing plants. The sensors are cartridges, and when they bind, when this thing binds to the sensor, let me see here. Yeah, when these bind to the sensor, they don't come out. So it's a one-time use. So it's a 30 rupee use and throw. So the basic instrument cost is about I would say somewhere around 30 to 40,000 might be the on the market price, depends on the commercial angles to it. We can make it for 10,000, 15,000. But these sensors are very easy to make. I call them garage sensors. You have a garage, you have a Bunsen burner or a butane flame, you have some pots and pans, you have a stove, you can make these sensors. It is that simple. It is that simple that a 11th standard student, actually my daughter, could make those sensors after a 3-day training. So the idea is that we transfer the technology to local entrepreneurs who make the sensors. From a central location, we supply the instruments, and we maybe make some money from the local entrepreneur gives a part of whatever his profit is. But as I said, very easy to make, very deployable, wide-scale deployable, but placed at a slightly a higher level than the housing society or individual customers.
Hi, I'm Manish. I coordinate the Arsenic Knowledge and Action Network. We work on addressing the challenge of arsenic in water. I was interested to understand how many samples can this device test? Because as far as I know, the Merck field testing kit, which is usually used, one device tests around 100 samples. We need to change it once again.
Here, the present technology that we use, it does only one test. It is not a colorimetric sort of vial-based test where the reagents can be used multiple times, I may say. So this does have that it is only one test. I mean, one test meaning one positive test. If you don't have mercury, then you can use it again. But if mercury is sensed, mercury or arsenic, then you have to dispose it and change it. Okay, so I think they should be done. And next up is Rajdeep.
Okay, so am I audible at the back? Okay, fine. So Soumya just now showed you how he has the ability to detect heavy metals, which is arsenic, mercury, lead. But what we are trying to do is measure only arsenic specifically, whereas that one will detect for you all the heavy metal together. So any one of them you cannot individually detect, is what I understand. So of course he set the stage that arsenic is a toxic thing. So we don't have to emphasize that. The problem is it's colorless, tasteless, odorless. So but it's deadly, and all of us know that it's a menace in these parts of India, northeastern part. The problem is arsenic is omnipresent. It is there in the reservoirs, rocks, so it is leaching out, and the number of affected regions is growing. are tests, methods, which have been in development and already used, but they suffer some serious drawbacks. These tests require long measurement times of 30 minutes and involves generation of arsine gas from arsenic, which is a poisonous gas in itself, and also it uses mercury bromide, which is another hazard to deal with. And it has interference problems, like phosphate has a similar chemistry in some sense with arsenic, so that if it is present, it interferes. Now, so what we wanted to do is develop something which is non-toxic, as a fast detection of the order of minutes, and with no interference. Okay, so what we developed, we went into the chemistry and developed some molecules with gold nanoparticles. So these are gold nanoparticles which are our sensors with some molecules attached on them, which is an analog of vitamin B12, that's why it's written vitamin B12 analog, which is on its own, looks like this, individual particles, but whenever there is arsenic, there is some coupling, which I'm not going into the details, which happens in the solution in a cuvette, and that gives a cluster of particles. So essentially what happens is, as you increase the arsenic concentration from no arsenic to 0.5, 10, 100 ppb and so on, the cluster size increases. So basically you're sensing material, which is this particle, small particles, grow in size. Okay, and that happens within a fraction of a minute. In fact, up to 3 minutes, the reaction is complete. Okay, so that gives us a basis for detection of arsenic specifically, and this reaction is specific only to arsenic plus 3, which is the more toxic form, rather than arsenic plus 5, these being the two most common form of arsenic. Now, so we have a way of detecting that, because this cluster size increase causes a shift in the color of the solution, not color so much in the spectral signal, so we have a light source detector to detect this. And we find, interestingly, that we can go up to, and we find that you can go from 0.1 ppb at the lowest to up to about 100 ppb, you can have a nice detection. And here I show as a validation that this method, which is of the order of minutes, can reproduce data of centralized lab facilities like absorption spectrometry or mass spectrometry. And this is a test that how a blank water solution which has no signal, if you add various of these interfering agents, copper, iron, calcium, zinc, which are common metals with which arsenic coexist in nature, or other interfering ions, including phosphate, doesn't give any change in the signal of water or mixture of these ions. But when you have arsenic only, there is a large peak which is about this high in the absorbance spectra. But when you mix all these ions at a concentration of 10 ppm, which is 100 or 1000 times more the arsenic concentration being 10 ppb, even at a 1000-fold more concentration, mixture of all these ions don't give any change. And that's seen in the spectra here is one proof. There are many such graphs. So basically it tells us that it reliably detects arsenic plus 3 to the lowest level of 0.1 ppb up to the highest level of 100 ppb, even if there are all these ions present all together at a concentration level of 1000 times. Okay, so we went ahead and tested some real water samples, starting with the water in our laboratory. It had 0 arsenic. Powai Lake water, 2 samples, 0 means undetectable. Another had 1.3 parts per billion arsenic. And the Mithi river here, which is in Mumbai, a very polluted river, and 17.4 ppb of arsenic, which is above the WHO recommended limit of 10 ppb. Okay, and this again reproduces faithfully the data of a costly spectrometer-based, mass spectra or absorption spectra-based data. So it reproduces the data exactly. So just to conclude, we have been looking at, of course, there are things like we have to do miniaturization, power supply, etc. to make it on field. Then parallelly, we are dealing with another system which is easier probably, but little less sensitive, is a traditional method of color change because of addition of some reagent, which is just 2 reagents you have to add. So instead of adding the gold solution, if you add these two reagents, then there is a visible color change if arsenic is present, in this case arsenic plus 5. And that color change you can, what we are starting to work now last 1 or 2 months, you can map on a color strip, and you can, what many others have shown, we have not yet reached there, you can do a RGB analysis and you can faithfully get the concentration. So maybe we can take a picture and map the color through the RGB coordinates and give the user the concentration of arsenic. This reaction to develop the color takes 7 minutes, whereas the previous one takes 3 minutes. This gives only arsenic plus 5, previous one gives arsenic plus 3 and total arsenic, so arsenic plus 5 also. Previous one has no interference from anything, whereas this one has an interference from phosphateate, which we have to overcome. So there are pros and cons, and of course the previous one is sensitive to the extent of 0.1 ppb, whereas here lowest detection limit is about 2 ppb onwards, and you cannot get really, is intervals of 10 ppbs. Okay, so that's the bottom line. Cost we can discuss later. It's reagent cost is 5 rupees, cuvette cost is 20 rupees, and so I'll end here saying that there are two systems. One is the gold particle reagent based systems, which we have very accurate and precise measurement of individual toxic species and total arsenic, whereas we have lately started with this second system, which is visual color based, but that has lower precision. Thank you.
So if there are questions, a quick clarification. Ajit already has taken up more than the share of.
I had one presentation.
Hello, sir.
Sorry about that, but I'd love to have some.
Hello, sir. Good afternoon. Nice to hear you. It's a nice presentation. Sir, I just wanted to ask you, you have tried on only gold or different metals you have used for that?
We have tried silver also. That gold work we have done for about a year. And I must mention Prithvish, who would be there in the audience. Prithvish, somewhere there?
Prithvish,
Yeah, Prithvish, he has done all this work with gold and got these beautiful results. Previously we had done silver with another student, Amandeep, who worked about half a year. Silver also has this property, of course, of surface plasmon resonance, but with silver the aggregation is much more. So we could measure 700 ppb to 3 ppm. But our point of interest is below 100 ppb, because the drinking water standards in India, Bureau of Indian Standards, is 50 ppb. WHO standard is 10 ppb. So the lower limit is picked up very nicely by the gold system, whereas the silver, it aggregates much more. The chemistry is almost same.
Yeah.
So it can give you in the ppm level.
Okay,
Few ppm. So
because it's gold, so
I think this discussion can be taken offline. So we have to stick to time. One more question and clarification rather. Right here.
Sir, with respect to the cost, you had mentioned something earlier. What is the cost of the device?
So cost of the reagent is about 5 rupees, which includes gold salt and the vitamin B12 complex and the chemistry that we have added. Cost of the cuvette is about 20 rupees, and the based on the lifetime of the detector, the cost comes out per sample used is about half to 1 rupees of the light source and the detector. So that comes out to be about 30 rupees.
And the detector?
Of course, it doesn't include other costs like probably disposal and etc. But these reagents are non-toxic compared to the current field tests, which don't work because they have arsine gas and mercury bromide. So they have their other problems. And the time of measurement is 30 minutes, 20 to 30 minutes. So here you can make not only one measurement, you can track over time, and you can make dynamic measurements. And same can be used again and again because it's a solution.
Right, right. Okay, thank you.
Okay. So.
Okay, thank you.
So now, Shuparna.
So I'll be presenting our work on characterization and treatment of grey water. So this is the work we are doing. Several colleagues from CAC, myself, Professor Sanjeev Chaudhary, and Professor Anurag Garg. And I'll be presenting the results. So grey water, as you already know, is wastewater without the toilet water. So it is almost comprised about 75% of the wastewater. And so there is significant potential, since it is less polluted, there's a significant potential to treat and reuse this wastewater. And so the objective of this research was to look at grey water characterization and to look and to analyze the performance of a grey water treatment plant that is in the campus, and to fabricate a novel bioreactor and to compare its performance with that of a plant that is already existing in the campus. So this is the grey water treatment plant that we have in IIT Bombay. I'll be referring it as GWTP. So it is based on a sequencing batch bioreactor for removal of biodegradable organics. And it also have tertiary treatment units like the activated carbon filter and the pressure sand filter, and then 2 steps of disinfection using chlorination and UV. This is the plant that we are looking at performance, and this is that's a 100 KLD plant. And this is our prototype. This is our reactor that we are using. It's a 2.5 liter reactor working volume RBC. That is a rotating biological contactor, which is often used for wastewater treatment. However, this is not a simple RBC, so we have modified it. There is a filter here, so it's a fabric, non-woven fabric filter that is put at there. So this filter, while the rotating discs develop biofilm that will treat or remove the biodegradable organics, the biosolids will be removed by the non-woven fabric. That is the idea. So we will have, in fact, growth of biofilm on the fabric itself that will facilitate the filtration process better. So that's the idea of this novel bioreactor. And these are some of the characterization results. I've put the mean value and the range we have found by analyzing the system over about 4 to 5 months period. And what you see is in terms of the organic content, this is similar to weak to medium strength sewage. But when you look at the nutrient levels, it is much lower, almost 4 to 5 times lower than what you have in sewage. That's one of the key things. And the other is the coliform count is 3 orders of magnitude lower. This is the difference between the grey water from the wastewater. This is our RBC system. We have started it by adding nutrients because the nutrients that were there were not sufficient to create the biofilm growth on the discs. So once we have started it up, you see the fabric is also effective in filtering out the biosolids. And this is the comparison of the performance. This is the inlet, this is the RBC outlet, and this is the GWTP outlet from the plant that I showed, which is a multi-unit plant. This is removal of total suspended solids. This is the inlet, and this is the outlet. This is 4 to 5 months data depicted in terms of box and whisker plots. So what you see is that the RBC performance is much better for removal of total suspended solids, also for turbidity removal, and also for COD, which is a measure of biodegradable organics. Although our system is a very simple system compared to the multi-unit system that you saw. In fact, for the GWTP, we found that the effluent was often foul-smelling, and it also had problems of foaming associated with it. These are probably due to nutrient deficiencies in the system and because of the cycle in which the system is being operated. Whereas in the RBC, we found good performance consistently in terms of all the parameters that were measured. We'd like to acknowledge the funding from Tata Center towards this project. Thank you.
It's really important, both of the gray water studies, because so much had been taken for granted that it was the black water that was the hazard, and gray water could be reused pretty readily, as it is in rural areas. But I was curious, as to what the level of treatment? Do you have a double chlorination? Is it pretty, going to tertiary, is a fairly high level of standard, whereas in a rural area for reuse, would you have a strategy that would have an intermediate level of standard, or would you say no, it really has to be at this level for safe human contact?
See, what we find is that in fact, even with our simpler system, we could achieve the treatment better than the multi-unit system. So what I'm trying to say is that even simpler systems can give us a solution of treating grey water. It is just realizing what are the differences in characteristic and accordingly designing the systems to take care of the parameters. We have to make sure that the systems are operating properly rather than just installing just all the type of systems we can think of. It is more looking at the operation also.
Distinct privilege and honor to invite Professor Westbrook. Let me see whether I can find where you present.
Okay, thanks very much, and thanks Professor Mukherjee and Chintan for including me in the panel. It's a great pleasure to be here after, I think, some 4 years roughly that we were here for an inaugural type of session, and it's terrific to see all of the really superb work that's underway at posters and projects here at IIT Bombay, and I'm learning an enormous amount. Our team has been looking at the village water planning and particularly district scale water planning in Maharashtra with the government of Maharashtra and its current Jal Swarajya 2 program with the World Bank. And as part of that program, periurban water problems were flagged, and a selected small sample of villages and projects undertaken. But the sample was so small it led us to wonder, what's the bigger picture of periurbanization in Maharashtra? And in particular, let's see what the role of a district could be in planning for such settlements, which we perceive to be on the scale not of tens, as in the current pilot project, but hundreds and possibly thousands. This is our team, and the good news is that everybody with the blue outline has graduated. So that's I think, inspiring for everyone. And the person in the middle here, Rebecca Hui, she was the Tata Fellow most actively engaged in the periurban study. We just had a paper accepted this week in Geoforum in a special issue on visualizing undisciplined environments. And the periurban settlements are really exemplary for that idea of what's an undisciplined environment or perceived to be such, and we wanted to bring more discipline to the study of them. The problem is very ambiguous, difficult to characterize, but these are believed to be the fastest growing settlements in India. And if you take them seriously, then you would see that India is not lagging in terms of the rate of urbanization worldwide, but rather has a rapid pace of urbanization, but it's happening in settlements that are classified by census terms as rural. So this whole categorization of and dichotomy between rural and urban is flawed and needs to have these intermediate categories of periurban, urban, and other hybrids to really move ahead towards a more ground-based type of planning. Periurban areas have special water supply and sanitation problems. They've got an enormous amount of floating population that increases water demand, different types of water demand. They face different types of contamination, water quality issues. And particularly as water supply increases in such areas, drainage is aggravated. And so drainage and liquid and solid waste are some of the key hazards here. The current competent authorities for planning and periurban settlements are the Zilla Parishads, which are not prepared to take this on in either planning terms or in terms of professional and technical capacity. So the question here is, how could that be enabled so that districts are able to do the job as the metropolitan regions start to engage and annex some of these settlements over time. So to answer this question, our goal was to develop a spatial framework, spatial line of analysis to show how these could be brought within the rubric or umbrella of water supply and sanitation planning. It involved a transect analysis on the ground to all the major highways in Pune district. Involved a lot of mapping of demographic and water and sanitation variables from a variety of both census databases, but also have developed a mobile app that's being deployed in really comprehensively in all the villages of Pune district, also Aurangabad. In the joint distributions, these are joint distributions of settlement size and water and supply and sanitation conditions, we start to find some real problem areas. The Class 6 town, which is in the range of the smallest level of census town, has consistently the poorest conditions, whether it be drainage or water infrastructure. Then we see on the right-hand side here, though, a lack of, rather a different pattern of a problem where wastewater is conveyed in open drains, which is not vary by settlement size at all. As settlement size increases, you'd expect to be able to have a parallel type of drainage emphasis. That's not happening. And so the drainage is going to be a key problem here. This initial mapping led us back into the field with a set of sampling interviews in about 30 villages to ask what matters to each of these screened areas as periurban in terms of their aspirations and perceived priorities with respect to water and sanitation. When we map all of these patterns together, we find the following. 4 major types of periurbanization in the district. So it's not one type, but rather a strong association with MIDC industrial locations along highway corridors. All block towns have periurban types of patterns of development, as well as the megacity, in this case Pune and Pimpri-Chinchwad. We'll put it together here. Of the 1856 villages, approximately 10% are periurban. 186, we have the 4 types. So then once we start to identify these different types and patterns, we can start to then say, well, what are the conditions within them, and can we develop some diagnostic indices? We did 2 of them. One was for the overall conditions, to say from a scale of blue, which is in good condition, to villages that are in a red zone with a poorer or lower level of sanitation and reliable water supply. Here's what we get in terms of the patterns. The patterns are fairly complex, so it's not simple gradients that one might expect of distance from a urban center as being the basis for need or sufficiency. Then we went to the greatest need question. Where are the dire situations? The places that have, and the 4 criteria for this were no latrine, no bathroom, drinking water away from premises, and wastewater, no wastewater drainage. So if you're lacking those 4 things, it is very deficient. The good news is that the periurban villages were more in the intermediate level, but the bad news is that it's truly the rural areas and remote areas that are in the most difficult conditions. But we can then take these data from the cartographic standpoint, and with the districts, we say, well, here they are. List them out, and for screening purposes, we can strategically go to those villages to tap in and see what the ground conditions are. We're going back and forth between ground-based and cartographic analytic approaches, and this is just this last week's ground-based check with a village that was in the lowest category of the Water Supply and Sanitation Index. Again, we found, to our surprise, somewhat, that periurban villages are not in the worst category of conditions, but rather that the periurbanization can lead to improvements in water and sanitation if managed well, if planned well. So what do we have in the way of an agenda carrying forward? Pune Zilla Parishad is interested in picking this up systematically. The Pune Metropolitan Regional Development Authority also sees this as something which they could look at for at the scale of 100 villages, again, rather than single case studies. There's an opportunity to look at multi-village and cluster planning, not just one by one, but sub-regional types of plans. This will require a lot more sophisticated geospatial analysis. We have some statistical work that we'd like to launch on multi-level spatial statistics, much better population forecasting. None of the current population forecasting methods are capturing the types of dynamics of rural to urban migration or periurban migration. And then finally, the incorporation of remote sensing analysis with the more cartographic approaches. We think we can move from the static type of rendering that's useful for planning at one level, say annual planning, to more dynamic forecasting tools that would have a multi-year, long-term strategic planning value. And then finally, the periurban is perceived to be a problematic type of space. And it comes, we found from historical analysis, from an association in its earliest use with apartheid South Africa. If you ask where was the term periurban most frequently adopted, it was in South African settlement policy. So this accounts for part of the negative associations. We think that the critical participatory planning approaches that colleagues are doing in the social sciences, I think Professor Eldo and his team here at IIT Bombay did similar work of this sort, published in Land Use Policy. We'd love to see the kind of collaboration that could happen there between the ground-based participatory planning approaches and these more district-scale analytical approaches. I think they together have a lot of potential. That's my 3+ minutes, other than to make a pitch, since this is the world of pitches, for the geography group that will be coming at the end of the time. Geography matters, and this place-based type of approach is really exciting in India. Thanks very much.
Just one question from here.
Yeah, just one, yes, please.
So when you talk about peri-urban locations and water supply, sanitation there, are you looking at also informal water supply which exists in peri-urban areas, especially tanker water supply and other such informal?
Yeah, very much so. And the this analysis is based on some historic data, but the mobile app surveys are all getting contemporary data that take up different tanker systems, including the state-based ones and the informal practices as well. Thanks. Yep.
I just had one question as well. Here.
Yeah.
What sorts of dynamic forecasting tools are you referring to move to in the future?
Some of them, we've actually started with one, but it was going to take a lot more work to develop agent-based modeling type of looking at the way in which population movement and other inflows into the system are going to be projecting out into more simulation of spatial growth patterns. But, yeah, simulation modeling, basically. Thanks.
Thanks, Professor Westcott. So now let me invite Professor Rohit Karnik.
Great. So thank you very much, and thank you to the organizers and all the participants for such a beautiful and inspiring symposium. So today I'm going to talk about some of our work that we've been doing on exploring the use of plant xylem as a natural water filter. And the person leading this effort is Kritika, who's the Tata Fellow on this project. So we all know that there's a lot of issues with waterborne diseases and tied up to sanitation and access to clean drinking water. And this burden is largely borne by people who don't have access to the technologies or access to clean water. And there's multiple barriers in this, starting from sanitation and pollution source control, as well as treatment at different levels. And the last barrier is at the household level, and it's been shown that it is effective in reducing the incidence of waterborne disease. But there's several challenges here related to awareness of water quality and sanitation and other issues, affordability, access to solutions, and also social acceptance. So in this context, what we are exploring is these naturally occurring membranes in plants. So in school, we all learn about this process of transpiration, where water is taken up by the roots and it's driven by evaporation in the leaves, and it goes up to the plants. So what happens is that this process actually puts water in tension. And so the plants have to evolve these very intricate structures, which are called the xylem tissue, which have these membranes whose function is to trap air bubbles. But the question that we asked is, can we actually use these naturally occurring membranes for water filtration? And if we can make filters from these naturally occurring membranes in the xylem tissue, they would be very simple to make because they already exist in nature. They could be eco-friendly while adopting sustainable practices, and basically the wood that we use for this is the wood around the valuable wood, so low cost and kind of less desirable wood, which can also be further used for cooking or other as fuel or other purposes. And then it could be cost effective, where the wood itself for one filter element costs around $0.01, and with the processing and other costs included, this could be in the order of a few cents or a few rupees, on the order of 5 to 10 rupees of recurring cost. And so maybe there's potential to address some of these challenges. So several years ago, we had done proof of concept experiments using a small piece of pine branch, showing we can filter water and then also remove E. coli bacteria with good effectiveness. And at that point, there were several challenges because this material had never been looked at from the perspective of engineering, only been studied by biologists. And so there were issues like if we dry it, it gets blocked, but of course we would like to have shelf life. Then in these experiments, we had very small areas and low flow rates and very small volumes processed. So can we get to a more practical scale? And we had no idea how this would work with actual water samples, as opposed to like deionized water. And so through support of from the Tata Center, we are able to address all of these issues and develop a fairly simple process of manufacture that addresses these. So basically, it involves soaking in water and then in ethanol or another solvent and drying it, which preserves the ability of xylem to conduct water as well as to filter. We also looked at what happens, can we scale this by scaling the area, by scaling the pressure, and so on. And through support of the Tata Center, we are able to also partner with Himothan, who work in the Uttarakhand area with several hundred villages, and to set up both lab and field tests to be able to demonstrate filtration with actual spring water and even muddy monsoon water. And these are a couple of different tree species showing actual spring water with some bacterial contamination, and after filtering, we don't get any detectable bacteria. We also have support from JVOPS at MIT to partner with D-Lab, who do a lot of work in understanding the user aspect. And so some of the takeaways that we had was people were very enthusiastic about using xylem because they could relate to trees, and there's a certain level of skepticism involved with, or less acceptance involved with chemical approaches of treatment. So this was very appealing. And what we also discovered is that people who had lower income preferred a pay-as-you-go model, and they had a threshold of about 20 rupees per week of cost for paying for water. And people who had higher incomes actually preferred less. They don't want a frequent replacement, but something they buy, they pay up front and don't have to worry about it. So that is some interesting findings that we came across. And so what we are now working towards is taking this core technology, and then we envision a lot of different kinds of products that could be developed based on this core technology. And we have started exploring some of these ideas. So this is a filter that's developed for the lab. These are some prototypes that our D-Lab collaborators are developing. And if you look at the cost landscape, what I've plotted here is the cost per unit of water, and then this is the actual recurring cost. And if you look at all the replacement cartridges, they are a few hundred rupees onwards. But with Xylem, we have the possibility to reach into this space, which is in the few rupees of recurring cost space, while having a similar or lower cost per liter of water. And this is a survey from 2011 in northern India, where the barriers for buying water purifiers, cost was identified as one of the barriers, and awareness and acceptability, and all of these go hand in hand, because it's like a choice, like, do I think the need is significant enough to pay for it? And so with this, I think with the very low upfront cost in this pay-as-you-go model, we believe there's new opportunities that could open up in increasing uptake, especially in rural settings where the adoption rates are very low. And so we all know that in India, if you go to urban areas, maybe these kind of shampoo bottles will sell, but otherwise these sachets sell. And so this is a pay-as-you-go model, which has been very successful in this case. And then can we do something similar in the water space? And beyond that, there is several interesting aspects of this technology, which is quite different from other technologies in the water treatment space available. And so one of the things is maybe we can do local manufacture, and rather than having a centralized high-end facility, be able to involve local communities in manufacture and distribution, and at a lower and affordable cost. We have also found very high interest among students, and we didn't do much to actually promote any of our earlier work. We have just one paper published on this a while ago, but dozens of students, or maybe even hundreds of students till date, have kind of taken it up and done experiments with Xylem filtration. And so this might be a very interesting or very powerful opportunity to promote awareness through engaging students. Then empowering people to be entrepreneurs. So one of the things that, it's of course an experiment and an idea. I don't have any business experience, but if we can create a core technology that can then branch off into multiple directions, then maybe it empowers entrepreneurs to come up with ideas and to make different kinds of products. We have a lot of interest from people in starting companies, and actually there's some work in progress in here. And also in disasters or emergencies, because these are very lightweight and compact, they could be in the size of a wallet, airdropping them or just buying these filters and preserving them for use in case needed might be another opportunity. So that's all I have, and thank you very much. So we have tried multiple trees, but basically it's easiest to take it from coniferous trees. And then there is some other kinds of trees which could also be used, but it's much harder to construct the right, in the right form factor.
So if you use coconut tree for that matter, so I derive this question only because coconuts normally grow on saline water.
Yeah.
This salinity, when coconut as a fruit, it uses the saline water as sodium chloride. And when you take samples from coconut water, it is potassium chloride. Even the patients take that water as their intake for good and nourishment purposes. So if coconut has been used in this, coconut phylum issue?
So we haven't explored coconut. So one of the, with trees like that, my understanding is that there is active mechanisms involved in the desalination process. So there's a lot of work on, say, mangroves in that area to understand the mechanisms. But what happens is with those species, the xylem and phloem are bunched. And phloem has much bigger pores, so you don't actually get the filtration effect because you have smaller pores in xylem in parallel with larger pores in phloem. So in those cases, the isolation of just the xylem, which has the smaller pores that can do filtration, is much harder.
One of my friends, Dr. Bhavarkar.
Can we take this on offline, please? We have to actually. Hello. Chintan.
Okay, so let me talk about some more work which is actually in collaboration with Rohit and another colleague of ours in mechanical engineering, John Hart, on data for improved governance. Somebody asked earlier that, do we document challenges in our process? And so this is one of the examples where we have realized that the journey is longer than we had originally thought it to be. For this project, where we wanted to integrate the sanitation, water quality, and health data for improving governance, the first phase started with JVOFs, which is another center at MIT, and now some undergraduates are being funded by the Tata Center for the same ongoing project. So here's a question. So there are lots of people you heard are making census. And the census would tell you that there's something wrong with your water. Who should you give this information to? Should you give it to a householder so that they can change their behavior? Should you give it to a village? That's the Village Water and Sanitation Committee or self-help group or what have you? Or should you give it to the administrator? This may be a district or a state or now, give it to all of them is not a good answer because, yes, you could do that, but when somebody has very little water and not much option, to tell them that your water is bad without telling them what to do about it is not a good idea. It induces panic. So we're working in all three areas on the information side, but I'm going to tell you a story today only about the giving this data to the government. The good news is that there are a number of independent data bases and the processes to collect this data. So there's the Swachh Bharat missions, SPM data, water quality data in IMIS, there's health data in IDSP database and so on. The bad news is that it's not really very nicely organized, so it's very hard to fetch in bulk. And because it's hard to process, it's also not being used in governance as much. So we set out to put together one such database where there are these three institutional structures involved. So there's the sanitation institutional structure, the people who manage the water quality, and there are people who manage health. These are totally separate agencies, and they come together only when there's an outbreak for a brief amount of time. So we first ran from agency to agency asking for this data, and then soon realized that they are so busy that they really can't really give us a bulk data, even if it's public data. And so we ended up creating a group across India and the United States, a small group called Data for Improved Governance. These people wrote scripts, collected data, cleaned it, joined it, all of that, so that we can process the data further, either visually or through some analysis, and see what kind of insights we can gain. So as we did that, here's what we realized, that this is the top level sort of hierarchy along which you can organize data. For sanitation, you have data at household level as to what is their infrastructure, what is the village level ODF status, and the village level statistics. For water quality, you can get to know what are the sources, what are the sanitation survey of sources, what are the field test kit and lab test, etc. And then for health, you can get to know about outbreaks at a reporting unit, which is at the hospital type of a level. Now, one might say, well, but the data is really in poor quality and all of that. That's a different question. But this is how we have integrated this database for the state of Gujarat. So now there are several problems. This is where the breaks, the sort of slowness in moving ahead comes. First, the administrative units have a mismatch. So if you look at this graph, and if you look at the number of households in the water quality database here versus SBM database here, they should sit along the diagonal because they should be the same. But SBM database has more households because it's a more recent database. Similarly, the jurisdictions in one database, a particular village is one habitation, whereas in the other database there are multiple habitations. The names have some spelling issues that we need to correct. Their credibility of entries, there are these multiple sort of gibberish strings that are there that computers can detect better than human beings can. Administrative units are changing over time. There are different base units. So health, for example, the reporting unit is a hospital, which you can say, well, by their location, they are close to a certain village or a habitation. But there's no guarantee that person from there will go to the very same hospital. So there's that kind of an issue. And sometimes the data is not complete. So if you just look at 3 districts, all of this gray, if you put together the data, all of the gray means there's no data. So what do you do? So what's the big picture is that if you take a well-known framework that that's used globally, that connects drivers of sanitation to the state of water quality, to exposure to unsafe water and therefore outbreaks, the colored boxes, there's one box missing here for some rendering problem. The colored boxes are the ones where we have data. And these lines mean that we could infer something about these other boxes. But this is the journey we're on. So right now, we realize that we need to work at a smaller unit. And a district administrator in Ahmedabad has agreed with us to let us, to give us their health data and try to work with their offices to understand what leads to the data hygiene issues in the first place. And could we create processes so that the data hygiene can be better first? And after that, could we then develop what are the requirements of a tool that can be built on top of such an integrated database so that an administrator can make better decisions? So that's all I have.
Yeah, questions and clarifications for Chintan?
How do you go about addressing this data inconsistency and incompleteness issues? Do you have any thought process on that?
So right now, nobody actually looks at it to even see that it's incomplete. Our idea is that at a district level pilot, we will, the first set of tools that we can write, very simple tools, would be to just tell the administrator which data is missing so that they can go after somebody to populate that data. And then some of the inconsistencies, we can do it through code. By writing software-based checks. That's the lowest hanging fruit here.
Okay, thank you.
Any others?
There's one
yeah.
more. Yeah.
The reason the data is typically missing is because nobody is using it. Once people start using it, the missing data problem will go away. So what would be some of the initial example applications you have in mind?
Yeah. So the application that has the greatest traction when you talk to administrators seems to be managing outbreaks and predicting outbreaks. Ultimately, based on, if some indicators are worsening, then if you can tell them ahead of time that, this is a zone where there should be greater due diligence in terms of the sanitation audits and all of that. That's the application that even that appears to have interest across all 3 agencies. Everything else, they say, yeah, that's nice to have, but that's not a part of my job, rule book, so why would I do it?
Okay, last question. Right. So.
Hi.
Yeah, front.
Titus.
Oh, yeah.
So the question is, like, I'm continuing for where the gentleman left. So one of the things is how do you get acceptance? The better you accept, the better the quality of data. So one question is, using things like gamification, having people to say, if you do it right, this is what you give. And then go to the agencies as government or private sector saying, let's try to get more out of it. Is that something that you consider? Because I think that free things are very well liked by people, especially we as Indians, we like free stuff. So if it's something, if you do it, we'll give you something free. It's something that allows for quality of data, which really goes across all the solutions we talked about. So, and if it's fundamentally having good water is important, I'm sure we could do some gamification stories in it. So I don't know what they are, but I'm just thinking, is that something that you thought about?
Yeah, so I showed in the first picture, I said, who you give the information to is a question. Gamification has a lot of potential. The state level administrator is not ready for a game yet. But the village level NGOs are willing to play a simulator to see how their limited budget can be allocated to infrastructure versus testing versus information dissemination and what could be the impact. So we're trying to build a game there.
So, okay, so I hand it over to you, Chintan, to take us through the next part of this session.
All right.
To depress the salinity levels in water as a commodity. That's why I was asking whether coconut xylem has been specifically used so that better quality of water also can be seen.
So I think just getting back to the question, the functions are different. So we are using xylem as a structural element, whereas the functions of changing the ionic concentrations, they are more specialized and carried out by live cells. So those are two different phenomena occurring in different systems.
This xylem filter, does it require to be treated with something, or you can use it raw filter as is?
So raw one can be used, but it won't, if you dry it, it stops working. But also there is considerations with the raw filter, like for example, is it disinfected or not? And it has, initially if you don't wash it, it will have sap. So then you want to make sure that you wash out the sap before you consume the water. So there is considerations like that, which, and from the quality controls perspective, it makes sense to have some standard process, which will ensure that you don't have the original sap and you also disinfect it before it's used.
Are there any dimensional criteria for the filter? The thickness should be a particular...
So there is, actually it depends on the structure of the xylem, and it's very interesting structure. You have tubes, which are parallel tubes, but the tubes don't go all the way. So these tubes are connected through the walls. And so we cut a section in this way, and if the section is thicker than the length of the tubes, then you get filtration. If it is thinner, you just get water flowing straight through the tubes, and you don't get filtration. So that length scale tends to be in the range of like few millimeters. So if you have a slice which is say 2 millimeters, it won't filter. But if you have something 5 millimeters to 10 millimeters, then it will start filtering.
And also perhaps it depends on the type of plant that you use.
Yes.
Okay.
So in conifers it's shorter. If you go to flowering plants, those tend to be quite large.
What is the life of the filter, the general life?
So this is kind of designed with a few days in mind. And what happens is that there's an interesting phenomena where the polymers, the natural material, organic matter from within the xylem, it will dissolve and redeposit. So over a period of time, it actually stops flowing water. And so the idea is to use it to process, let's say, 50 liters or 100 liters. And then over a period of time, basically it blocks. And then if you, of course, leave untreated wood in water for a very long time, it will eventually get degraded naturally.
Thank you.
All right. Good. Okay, so let's go to the part 2 of this session. We have a little different format for you for this. So instead of you picking our brains, we want to pick your brains. The premise for this is that, the realization is that water domain, as you would see, needs a lot of collaboration, because there are all of these different types of contaminants and each person is working on one type of a contaminant. There are so many dimensions of this problem, and there are so many people working on pieces. So could they talk to each other, and could we create a community around it? So we're going to go into a short generative session. I'll give you an outline of it, and then we'll be able to get up and move around a little bit. So here's the plan. So the agenda is to synthesize sort of the current research that people are doing in this room and the future research that they'd like to see with respect to water domain in India. On the next slide, I'll show you what the session, how we'll set up the session. And then the desired outcome is that by the end of the session, there'll be some kind of an online forum that one of us at IIT Bombay and another at MIT can help coordinate so that we can work on topics related to water going forward. Part of the inspiration for this comes from, say, arsenic network or fluoride network and so on, because it's such a distributed problem. So here's a plan. So after this setup, there are 4 different areas roughly that we have designated. The water use, that's that white blank poster, where water sufficiency can be one set of problems, quality can be another set of problems, purification can be third set of problems. So do you have enough water? Is it clean water? And if it's not, can I clean it somehow? Water pollution can be industrial, agriculture, domestic, etc. There's a whiteboard on the other side. Water and geography, so this could be problems of groundwater, surface water, urban, rural, peri-urban, geography-based problems. And then water and health. So this is the connection between sanitation, water quality, and health, as we were talking about. So waterborne diseases and so on. So there are 4 boards here. We want to take first 10 or 15 minutes for you to jot down your ideas. So we have a whole bunch of sticky notes. They come in 2 colors. In the yellow notes, let's just write what are the current problems you are working on, and put your name on the in a corner so we know who to contact. And on the purple one, just say what problems we should be working, we need to be working on. So that what are you currently working on and what we need to be working on. You can write as many post-its as you want. After that, we're going to do a little synthesis and report. So we have designated ourselves as people who will report. So we'll do that report out. And at the end of all of this, there will be an online community resulting from it. That's the plan. Okay? I'll put this slide up again. Let me also say that water is an issue that affects everybody, but if this feels like not your thing, we will not be offended if you choose to leave. But we'd love for you to stay, because it takes all of these stakeholders to solve an important problem. Okay? So can I just do a very quick show of hands just to make sure that who would feel that their central issues are related to this sufficiency, quality, and purification, like water use. Can I see show of hands? I just want to make sure that each group has at least enough people. Because then you can go to the poster for during the synthesis part. Okay. How about pollution, water and pollution? Who feels that they are related? Okay, there is a good group here. How about water and geography? So ground versus surface. Okay, there is at least a small group. How about water and health? So water quality, health. Okay.
Some people are raising their hands.
Yeah. Okay. But anyway, gravitate to, put your stickies up and then gravitate to whichever poster that most resonates with you. Shall we take a minute's break, 2 minutes break while everybody gets their stickies and pens? And we can have the lights up, please. Oh, yeah. Okay. If you think of a problem that actually belongs to more than one category, feel free to put a sticky in each of them. Yeah, and there's a lot many more stickies. So if you need, just raise your hand. Yeah. The yellow sticky is on about what you're working on. The purple sticky is about what we need to work on, according to you. Yeah, yeah. If you're not working on any of it, then you just say what we need to work on. Walk around or just direct our friends to put it up wherever you think they need to go. Yes, on the side, your name in the corner, please. All right, so we have 4 poster boards, and I encourage you to migrate to the poster board of your choice. So the first one, the water use, is going to be summarized by Rohit Karnik and Rajdeep Bandyopadhyay over there. Yeah. So we're going to take the next 5 to 7 minutes to just see what are the salient points. So if this is your passion, go there and talk to them also as they summarize. The second one on water and geography here is going to be summarized by Professor Jim Westcott if that's your passion, come here, hang out with him. The third one, water and health over there, sorry, is going to be summarized by Soumya Mukherjee and myself. If that's what your passion is, feel free to go there. And then water pollution over there is going to be summarized by Professor Suparna Mukherjee. So if that's your passion, go there. Okay, let's do the summaries and then we'll report on. Let me do
sanitation. Okay. And so let's switch a bit. So we have did a single platform bit on water run. Authenticity of that. Simple put no, should people gather around or we make it open?
So what we have in the water challenges is 3 categories here, water quality, sufficiency, and then purification. And of course, all of them are interrelated. In water quality, if we look at what people here are mostly working on, it's sensors, so sensors for chemical contaminants and microbiological contaminants. So that's the predominant theme of people who are attending here and participating in this. So there's people working on things like fluoride detection or bacterial detection, heavy metal detection, and then detection of water quality related to specific applications such as water quality in saline waters or water quality of water available for drip irrigation and so on. And then if we look at the needs or what people think we should be working on, so there are things more at the systems level. For example, we have several solutions in the water space, but how do we compare and understand which solution is appropriate? So can we provide, say, a village level test bed or some kind of a realistic test bed like that, which can help to compare different solutions and pick the more appropriate ones. Then another note here is very, it kind of gets to the point of water quality in terms of information. Like, how do we know what is the quality of water and is it safe to drink or for whatever use, and to know it quickly. So that's one major problem, and there's a lot of technologies that are being developed. But today we know that if we go somewhere and there's water coming out of a tap, we don't really, there's no way to tell in a minute or a few minutes whether that's safe or what the contents are. So we are still far off from real time and very quick information about the water quality. Then other suggestions are basically focusing on the assured ready technologies in the water quality space, and to kind of go towards more local solutions as opposed to top-down state-level solutions. So those are what people feel we should be working on. Also sensors specific to certain kinds of contaminants or elements. Then when we move to water sufficiency, there's very few people here working in that area. But there are people working on providing water to rural communities where there is fluctuations in the supply of water with time, with seasons, or water conservation. Also, very simple things like there's a note here which says my apartment installed washers to control water leakage or to control the water usage. Then methods of purification of water, low-cost purification of water. And when we look at what people think we should be working on, there are problems like overly contaminated rivers. So again, water quality and sufficiency are related, because if water is of poor quality, then you can't use it for many purposes. So rivers is one focus, education of water conservation. Then how do we minimize wastage of water? So things like ranging from leaky taps or leaky infrastructure to overuse of water. Like a lot of times we see when the clothes are being washed, the tap is full on and the water is just flowing away. So things like that. So how can we use water more efficiently? And can we do this at these like small levels, like maybe designing taps for minimizing leakage, or at a more systems level, so integrated resource management at the community level. Also getting water for water sufficient, the supply side, can we do like rainwater harvesting? And there's a lot of technologies to purify water, like desalination, that will increase the supply of usable water. And then also water reclamation and minimizing the waste discharge, like brine discharge, so there's zero liquid discharge systems. And I think, and judicious use of water in agriculture, which happens to be among the biggest consumers of water.
Oh, okay, fine. So Rohit has nicely summarized and elaborated. So I'll quickly add, in India, we have the major problems in contamination in terms of water is arsenic, fluoride, microorganisms, etc. So there is always a need of purification or removal of those contaminants. So, and that has to be done, as people have rightly identified, at both the point of views, household level and also community level. The scales are different, so the solutions would be different. There is already ongoing work, but more needs to be done. Some interesting notes on detecting hormones in water, which are not commonly considered. And I know, for example, antibiotics also, biomedical wastes. These are fringe cases, but nevertheless important. And then people have pointed out the importance of awareness, starting from children at schools, that they should be taught about hygiene and awareness of water, treated water. And of course, work on devices, membranes, filters needs to be emphasized so that they can be employed on a wider scale. So I think these are the main points that I see from these notes. Thank you.
Okay, well, thanks to our team for organizing these ideas and sharing good ideas. I think the first point that was raised was that the geographic framework really needs to be developed. If we think about these four, they're not just four of a single gradient, but rather you have different types of use, urban, rural, periurban, urban, on one side, and then you've got hydrologic systems, surface water, groundwater, but then the group said, well, the interaction between these and soil moisture conditions and the atmospheric climatological processes kind of off the map here. So, and then additionally, to these, the geography of water resources management is going to include the levels of governance. From international to national to the states, or states have constitutional authority over water. So we think that a lot could be done to establish a sophisticated geographic framework for water resources research. That would be the highest level of the contribution here, and it would be very exciting to do this in the context of India. In the work that's currently underway, we identified a few of the major themes, some bold ideas, new ideas, and then some omissions, more omissions from our discussion up till now. So in the case of urban and rural water, a lot of emphasis on the processes of rainwater harvesting and of urban water reuse, recycling, and treatment. Some creative work in the approaches to participatory water resources management, community-based water management, and as it relates to both flood hazards as well as water supply and water quality. The topic of groundwater was heavily emphasized, and that's probably appropriate, given that the surface water systems have a more established set of policies and regulations and scientific research than groundwater that, while it's catching up in scientific terms, is relatively weak in regulatory terms. So have a very strong policy in Maharashtra for the Groundwater Management Act, but implementation is, people don't know what to do. And that raised the topic of research on policy and regulation, regulatory strategies, and how they might be linked with behavioral change, and even cultural dimensions of water resources management as topics to be considered in the future. Some really exciting ideas about ways to link remote sensing, artificial intelligence for predicting future water resources use. So this kind of visioning out on a time scale of decades. It was an exciting idea that was raised as something that we should attend to. And then I think the group also had a good emphasis on some of the natural systems and that correspond with surface water and groundwater of watersheds, river basins, aquifers, and taking those types of research and categories seriously. Heavy emphasis by some on the very complex diversity, socioeconomic as well as physical geographic diversity of situations that affect which technologies will be pertinent or not. Suggestion by some that incorporating these dimensions of water resource geography into the curriculum would be welcome, and similarly a great need to advocate for data sharing across sectors, across scales and levels of government, because the data access and flow, while improving under the RTI context, is still, there's a long way to go in terms of ready access to data resources to address these pressing problems. I think I wasn't able to do justice to what everybody said, but we've got the record here and photographs of it, so a lot of promise. So thanks very much.
Let's hear about water and health. So what we see here is that in terms of people working on sanitation, there are really two sets of people. There's somebody working on fecal sludge management, and then there's a cluster working on in the Swachh Bharat mission context. So that's the defining what open defecation-free status means, adoption of toilets, behavioral change campaigns, and feedback to policymakers. So that's sort of the cluster of people working on. And then the suggestions are essentially in two large clusters. One are a set of people saying that we need a sanitation infrastructure that is more water efficient, so that connects to water use. And second is that it says that we need recycling of water. So if the infrastructure is not as efficient, then at least we have to do something outside of the infrastructure. What is interesting to see here is that sanitation infrastructure is viable only if the water infrastructure is viable. So that's an interesting set of comments here. And finally, there is the sort of the landfill water leaching into groundwater, which is a classic problem, but now augmented even further with this sanitation infrastructure, particularly if it's not proper.
One of the problems in the sanitation infrastructure is that improperly designed toilets are worse than open defecation. So that is one of the things that was pointed out in Tata Trust long back, but this landfill water sort of relates to that. Improperly designed landfills are worse than people dumping anything anywhere. People are working on waterborne disease management, both in the health, both in awareness building as well as some sort of a prevention angle. so that people have with low cost hand washing and disinfectants and building awareness. But at the same time, people would like to see that a better understanding of the microbial and viral contaminants of water, which can increase the possibility of diseases. Also, people would want to see that it is very easy to say that segregate black, gray and white water, but in a infrastructure which is already there, like in a slum, how do you facilitate separation of those waters? In new projects that might be already taking place, but in existing settlements, how can one facilitate that? That will be an interesting area of work for someone to look at the planning and looking at easy modifications to that planning, I guess. One very interesting, again, question has come up for people who move around, travelers. They go and drink water in various places. The water in various places tastes differently. It's not that everything makes them ill, but for someone it might make them ill. I mean, I am familiar with water of Bombay and Kolkata. Okay, reasonably pure water in Bombay and Kolkata might not make me ill, but something in Delhi might. Although that Delhi water does not have any microbes or anything like that, there might be just a difference in the salts and things. So, is there any way to look at that and sort of create a map or try to understand that process? From the drinking water quality side, there is a lot of work being done, as we could see from the presentations also. There are people working on sensors like I am, or people working on like myself or Rohit Karnik, who are working on sensing bacteria or sensing heavy metals. Rajdeep is working on that. Similarly, quite a few other people are also doing that. There are a cluster of people working on arsenic mitigation and also grey water treatment. What people would like to see is a more integrated system in terms of one side purification and sensing, in the sense that sensors which can detect sensors in a cluster which can detect a whole bunch of things, as opposed to sensor by sensor by sensor, and purification systems which can get rid of arsenic and bacteria, both of those things together. So, in a sense, people are looking forward to development of integrated system for water quality assessment and treatment. Anything else you can say, Chinmay?
I think those are the two main ones.
Digitized single platform data on water related to socioeconomic profile and health. Yeah, that is also an interesting. I mean, again, a water quality map with a socioeconomic profile, just not the geography.
All right.
Yeah.
Let's hear from the.
So I'll first go through the domestic water. So looks like we have researchers or people working on water quality and water monitoring issues and trying to improve the water quality at a domestic level. And people are also investigating the life cycle assessment of various treatment technologies. And there are researchers working on disinfection using nanoparticles, and also leak detection systems in public water supply systems and in large-scale water distribution systems. Sorry, this is unreadable. I can't read this. Okay, regarding what people would like to see is some studies on how much water should be made available to households. So water availability issues is of concern. And then the treatment of wastewater, better treatment technologies, better sensing technologies, and how to control the water pollution in the village level, and how to make the village people aware regarding the pollution in the water they are using. And people are also interested in looking at the quality of the domestic water and to understand whether the domestic water that is available is of proper quality for drinking, and also interested in waste contamination issues. And some have raised concern about the efficient desalination systems which can be used for drinking water purposes, treating water to drinking water standards, and regarding fixing of heavy metals present in water through. So as for the industrial wastewater treatment, so regarding current studies that are going on, so there is work going on in removal of fluoride, arsenic, heavy metals, and so researchers have been synthesizing nanoparticles for removal of contaminants and characterization and treatment of industrial wastewaters. Grey water is going on in IIT Bombay, and then ETP and STP plants are being used for generating water of reusable quality, and pollution monitoring practices for monitoring rivers and processed water. And there is industrial wastewater treatment work is going on in many places. And regarding what would like to be done is obtaining brine after desalination, brine from desalination, then use of alternatives to sodium hypochlorite as chlorinating agent, which can help for the industrial wastewater purposes, treatment purposes, then improving the efficiency of ZLD practices or increasing the use of ZLD, and more demand for market research on products for removing heavy metals. This is what one would like to see. And then removal of contaminants using algal treatment systems for refinery wastewater, and then better disinfection systems using nanoparticles. And for the agricultural pollution, so work is going on in water conservation and also better water retention, and work is currently going on crop disease forecasting, groundwater recharge, and water pollution. And there is work going on eutrophication happening in PD village, and also replacement of the excessive use of fertilizers that is being used with vermicomposting, so that the water quality is better and less of eutrophication problems are encountered. And regarding what people would like to see is better agricultural waste management so that the water quality does not deteriorate, and better management practices for crops that are deteriorating the quality of the soil. So better management practices for that. And then use of nanotechnology for enhancing agriculture, and then solution for rural irrigation through cleaner water for farming. And instead of building large dams, to harvest the water from natural resources and use these in the respective areas, and to improve the level of water table. And steps should be taken towards solving the problem of eutrophication and solid waste management. And some simpler natural solutions for cleaning water bodies, that is like lakes and reservoirs, should be developed, and efforts to support water conservation activities, particularly through rain-fed water. So these are some of the key recommendations.
Okay. All right, great. Well, thanks for participating. We will synthesize this further, so and create an online forum. So we have your names, so we'll go after you from there. It's time for tea. Thank you.